Hi, everyone, and welcome to the AWS Nordics office hours with me, Gunnar Grosch. I'm a developer advocate here at AWS based out of Sweden. And this is my weekly show where I bring on AWS experts to talk about specific AWS related topics and let you, our viewers, well, hopefully learn something new and get your answer or your questions answered on that topic. So if you have any questions, just pop them into the chat and we'll do our best to answer them throughout the hour. And this is our final episode of this season before going on a summer break. But don't worry, we'll be back after the vacation period, of course. So this week, I'm happy to be joined by Muhammad Sajid to talk about CQRS with purpose-built databases on AWS. So welcome to the show, Muhammad.
Thank you very much. Thanks a lot, Gunnar. Thanks for inviting me.
So we always do a quick introduction. So tell people about who you are.
All right. I'm Muhammad Sajid, and I'm a solutions architect at AWS. And I design and develop software solutions, cloud native software solutions, deploy them in cloud, do a lot of fancy things. And some of the fancy things you're going to see today, by the way, we will talk about CQRS and how we can use them together with the purpose-built databases. Other than work, what I do, actually, I play badminton sometimes. I love photography as well. And listen to audiobooks and whatnot. And there is no summer in Sweden, by the way.
Well, it's the summer period at least.
Yeah.
So I mentioned the topic of the show, CQRS with purpose-built databases, and we're going to spend this hour to explain what that is, because it might not be super obvious based on the title. And this is, of course, a technical show, so we're going to deep dive. Mohammad's going to show us several demos, see things in action. So let's start with what CQRS is then, Mohammed.
So CQRS means command and query responsibility segregation. So when we build softwares, we usually have either commands and queries. So what is a command? Command is something that we ask a system to do. It's an intent, and the system does it for us. But when system does something, actually system mutates the state of the system. So we either do some writing on the database, we do probably changes on the in-memory objects and things like that. But query, on the other hand, is something that does not do any changes, or it doesn't have any side effects if we talk in the technical terms more. That means we will ask our system to give us back something or return a query result, and it will not do any changes in the system. It will just go read something, a few things from the databases. It could be from reading from the cache, it could be reading from any memory DB or anything, and give us back. So this is the gist of today's session.
And to do that, then, do we need to separate reads and writes on the database level?
Actually, it's a very good question. I think we will definitely go a little bit deeper in that question as well. And glad that you asked it already. Actually, we can implement CQRS on different levels. Some people implement it on the model level. So what does it mean? It means we are only implementing it in the application layer. And we have models. We separate write models from read models. But this is like one level. And honestly, I personally suggest and believe that we should go all the way to the database level. Why? Because let's say if we separate reads and writes on the application level only, our databases are still single point of failure. And what if our database don't scale well? What if we do not choose the purpose-built database for the job we are doing? What will happen then? Then we will not be able to scale the databases on the database level. So that means there is no point like separating writes from the reads, because the main purpose why we do this is the scalability. Because most of the time, when you're working with some system, your reads and writes are not equal. Like you might have a lot of read traffic and very little write traffic. Sometimes you have a lot of write traffic and very little read traffic. So what you want to do, you want to be able to scale them independently of each other. And that we always do, even on the databases level. If you remember, some of the databases in AWS, we have, read replicas. We have primary replica, which is actually accepting reads and writes both. But then we have read replicas for reading only. So that's why I suggest we should actually go all the way to the database level and separate reads and writes.
And you mentioned purpose-built databases, and it's in the title of the show as well. Maybe you can mention a couple of those and how they are purpose-built.
All right, so actually I have a slide as well. I'll show you in a minute, the slide as well. Just let me share my screen. I hope you can already see it.
Yes.
So I will go directly into the purpose-built databases. Some of you might have seen this slide already because I already presented it in the AWS Summit Stockholm last month, I guess, was it right? In May.
Yeah.
So why purpose-built databases? The problem is one size fits all approach doesn't work anymore. We cannot use, let's say, relational database for every use case. Similarly, we cannot even use document database or even key value or graph database for everything. So each type of database has its own purpose. For example, let me ask you a question, Gunnar. If you are building a relational database, right? And you have rows and columns, you have multiple tables, you are normal form champion. Do you remember the first normal form, second normal form, third normal form? We used to study a lot back in the days. So what kind of database you will use? Definitely you are going to go towards the relational database because this is your data. This is how your data is structured. Your data is structured in rows and columns. You have joins, you have whatnot, multiple tables and things like that. But what happens? These kind of databases are not very good for the read use cases. Like if you have heavy read application. So that means you have to think about your access pattern. You also have to think about the size of your data. And that's how you choose a particular type of data, whether it's a key value database or a document database. In a document database, for example, you store JSON documents. So you have to think about what kind of data you have and what kind of database technology you're going to use to store that data. So that's why it's very important to actually think about right database for the job when you're storing the data. You will not store, let's say, relationships and nodes and vertices in key value database because this is a graph use case. You will not build social media application on a relational database. You can build, obviously, but you shouldn't. And that's what I mean. You would definitely use graph database for that because this is where you can actually traverse. You have relationships among different nodes. So that's why a purpose-built database is very important to think about. And by the way, today I will actually show you two very interesting purpose-built databases, and one of them is my favorite. Actually, both are my favorite.
Can you have two favorites?
Honestly, I have a lot of favorites among them. And for example, DocumentDB is also my favorite. I wrote a video course on DocumentDB last year, actually. So Ledger database is my favorite because I will show you a really, really niche use case where we will use Ledger database, and obviously DynamoDB, which is a key value database, and both document and key value database DynamoDBs. So that would be very interesting. Do you have any favorite, by the way, Gunnar?
Well, I think I have to say DynamoDB as my favorite. It's, as you said, it perhaps doesn't fit all use cases. There are purpose-built that you should use in certain use cases, but DynamoDB is such a great database option for serverless applications.
Exactly.
All right. So those are some of the purpose-built databases we have here. And I know when we talk about CQRS, it's quite often to mention event sourcing and that they go well together. Can you explain a bit about that, perhaps?
Yeah, that is a very interesting question. And honestly, we will not touch too much about event sourcing today. But luckily, I have a little slide about it. CQRS and event sourcing, they actually go hand in hand. It doesn't mean that we cannot have CQRS based applications when we are building event sourcing applications, or we can have them independent as well. But most of the event sourcing application, by the way, they need to have CQRS, because the way event sourcing applications work, they do not store the current state of your system in the database. What they store all the transition, all the events that are happening in your system. I will come to the events and commands a little bit later as well. We will go through them very quickly in a minute. But in the event sourcing database or in the event sourcing system, what we do, we store events. For example, if you look at the screen right now, you can see there is an example of a bank account. So when you have a bank account, what happens? So usually you have your current balance, right? Just start with some balance. And what do? You usually deposit something, and you can withdraw as well, right?
Usually more withdrawal than deposits, to be honest.
Okay, now you're talking about my bank account. I was talking about somebody else's bank account. I don't have any deposit, actually. Honestly, I get only one deposit, and you know when I get that.
Yep.
So when we deposit something, the system issues a command that becomes an event later on. So command is deposit, let's say $10, 10 crowns, whatever currency you're following right now. And when we deposit it, actually the balance changes based on the deposit. So the event sourcing system keeps on adding these events into the system. And that's how we build this current state. So we also call it active state. So this active states that you see on the right side is not present in any table. There is no column that tells you what is the current balance. The only thing that we have in the event sourcing system is these events, series of events, and from these series of events we can actually build the state. So this is what event sourcing system is. And CQRS and event sourcing systems or event sourcing pattern, I should say, they go hand in hand. And people, especially when people are building event sourcing system, they use CQRS for ingesting commands. All right. Yeah, this is about CQRS and event sourcing. I think we should also go a little bit towards the history. Shall we go like how CQRS started and what happened? What do you think?
Yeah, let's do it.
Yeah. So let me start that from there. So if you look at the screen, you can see a typical CQRS architecture diagram. We draw it in a way where we have a client, and then we have two different possible options. We actually can write something, and then we can also read something. So you might have guessed already that writing means this is the command side, and reading means is the query side. So when we write something, we actually use separate domain models than the models that we are going for reading. So if you look at the top here, you can already see the domain model is receiving the writes from the client, and then we are writing it in the write database. And Gunnar, you asked the question like, do we really need to have multiple or separate databases for read and write? No, we can actually do on the same database as well. But again, there is a problem that we will have a central database, which could be a single point of failure. And then that database might not be optimized for queries if we are using it for both writing and reading. So that's why we will definitely going to use database that are specialist for writing and then a different database for reading. So when you write something, actually it goes to the write database, and then we need to have then we need to send this data that we just wrote to a different database. That means we will have some kind of eventual consistency, or we sometimes also call it replication lag. And I will talk about those terms as well today. So when we do the projection, what happens? The projection could be anything. It could be a materialized view. Projection can also be just a copy of write side and sending it to the read side in a denormalized form so that it is much faster to query. So that means we need to think about eventual consistency as well. So eventual consistency means you will not see the changes immediately into the read side. The changes might take few milliseconds depending on which type of cloud vendor you're using. In AWS, we have usually single digit milliseconds transfer within the same region. So that is pretty fast. That is quite fast. And But still, some people think too much about the eventual consistency. Okay, no, we really need full consistency. We cannot live with eventual consistency. But if you look at Gunnar, almost everything in our life is eventually consistent. Even this show that we are running right now is eventually consistent. People are not able to listen to us exactly same microsecond level, right? There is some kind of latency. So
Yeah.
eventual consistency is pretty normal. We see it everywhere. Like if you look at the social media, we don't see everything when somebody pushes something on the social media. We see it a little bit later. So eventual consistency, I say we should embrace eventual consistency and love, learn to live with it.
So looking back at the previous example you gave then, so if I do withdrawals from my bank account for a millisecond or two, it might look like I still have that money in my bank account. Is that the case?
Yes. And this is most of the time, this is the case. Not only your bank accounts, I mean, when you do shopping, let's say on any e-commerce website, it takes time. And you might already receive the order, you might receive the order processing email sometimes, right? Because they are trying to do something behind the scene, because there is some kind of eventual consistency involved. With banks, you might have noticed we can even go into the negative sometimes, because banks do not want to block your transaction
Yeah.
for such a little amount. They want to make sure you are successfully able to buy things, and then they will offset it later on when you have more money in your account, end of the month probably, or the beginning of the month.
So, so we have a lot of chatter in the chat right now, which is great. We have a question from Nida. What about cost optimization if you're using two databases?
Yeah, actually, when we use CQRS, it's more cost optimized.
So
And you might,
how is that the case?
yeah, the reason is when you have, let's say if you are using both reads and writes from the same database. Now let's focus on the database part here first. What happens? You will choose the database bigger instance size, right? Because you want to support 70% of your reads and let's say 30% of your writes from the same database. But your writes are, let's say, not that much. Now you want to make sure you have two different databases, and then you scale them on an appropriate level. We call it right size the database. Okay. Second thing is, what about if you have database which is a serverless or pay as you go, or you're paying on demand rather than having a fixed capacity, or rather than having to choose how many instances you want and things like that, or what kind of instance size do you need? Still having different separate reads and writes will be will reduce your cost in the long run. Because now what you will do, you will optimize your database for reads separately. Now you will not think about write at all. Similarly, on the write database, you will optimize that write database for writes only. Now you will not think about reads. So now you're doing very fine-grained optimization on both sides, or both databases. Also, let me ask you, Gunnar, a question here. In this picture, you can already see the caching, right?
Mm.
Do you use caching on the right side? Very rarely. I mean, you
Yeah.
never use caching for writing something, because otherwise you might not get the right things from your system, right?
No, exactly. But I guess you use queues sometimes and things like that as a way. I'm not sure if we would call that caching though.
But queue is usually we use for load leveling, right? We can
Yeah,
also
or
use
for
queue for buffering,
decoupling.
yeah, or having like decoupled readers from the writers, right, or the publisher or subscribers decoupling, right? But still, we cannot call it caching, because it's totally different. But caching
Yep.
on the read side is very important, right? When we use caching on the read sides, we actually reduce cost, because now we are not even hitting the database. So that's how, if we have separate read and write databases, we can optimize the entire vertical of read for reading, and entire section of writing for writing. So that will reduce the cost significantly.
Right.
All right.
Yeah, one more question to bring up.
Yeah.
CQRS versus repository pattern?
Yeah, so repository, now we can go a little bit more into domain-driven design as well. So repository, in the repository pattern, what we do, we generally interact with databases, and we have some kind of repository that is doing all that. And if you are from, depending on what kind of programming languages do you use, let's say if you're using .NET, you might be using some OR mapper like entity framework, and then talking to SQL or some other type of database. But on the read side, if you use the same type of OR mapper or same type of repository, you usually get less performance because of this OR mapping or mismatch of between your model and your database layer. So what usually people do, they write separate reads, read repositories, and write repositories. So for the reading, they use sometimes even direct plain SQL queries. They don't even use any OR mapper in between. But for writing, they do it usually. But repository pattern we can use with or without CQRS pattern.
Right. All right. So I think maybe we should look at an example, right? Is it time for the first demo?
Yeah, definitely. I think we should, but let me show you the architecture that we are going to work on today.
Yes.
I think that is very interesting, right? So what we are going to do today, we will talk about commands. You will see queries, and let's look at the command first. So what is a command? So command is nothing but an intent a user is sending. All right. So I'm talking about the command. So what command means, for example, deposit. Let's talk about the banking example because we started with that. So when you do a deposit is a command, but deposit command can be accepted or rejected by the system depending on some requirements. For example, what if your bank account is blocked right now? Your deposit will not be processed. So this is called your command is rejected. But once the command is accepted, it actually gets into some kind of event store or event database. Then it becomes a fact. So events are represented as past tense. So this is something that cannot be changed. This is a fact of life now. So command is something that could be accepted or rejected, which is we generally say deposit or submit. But once something is registered in the database, then we call it deposited. Now it's in the past tense. Now it cannot be changed. This is the fact of the life now. So yeah, this is the command side. So 2 or 3 concepts that we have to remember. One is the command, one is the event that we already know. What is an event? Event is a past. And what about the query? Query is a third type of message in a system. So there are 3 types of messages: commands, events, and query. So query message is a read only. I mean, we can just ask the system, give us back some result, and then system will give us the result based on the query requirements. So in this architecture, what we will do, uh, if you remember from the previous picture, the projection part. So this is the projection part that is actually sending the data to DynamoDB. So what we are doing today, we will look at QLDB or Quantum Ledger Database. So we will be looking at a use case. I have already shown this use case by the way in the AWS Summit Stockholm. Similar use case we will look at it today, but we will see how QLDB can be used as an event store, because QLDB is a cryptographically verifiable and immutable database. And this is very important to have. This feature is very important for the for a event sourcing database, because immutability is very important here.
And going back to that example, then that means that we can't take one of those, say, withdrawals and just remove it from the system, which would increase your total on the bank account.
Exactly.
Yeah.
Not only that, I don't know who will trust on that kind of bank, if that is possible.
Yeah. Well,
So yeah,
there's probably examples out there, but hopefully people don't use that kind of banks.
Yeah. Let's not go in that direction.
No.
I think. So talking about trust, by the way, so trust is very important. Trust is very important in the system. So that means the customers or clients of such system should be able to even verify if their transactions have been successfully persisted, right? And your system should be free. Nobody should be able to temper it with anything. Like you should not be able to modify events that has been persisted. You should not be able to even add fake events or cancel certain events and things like that. All right, but does it mean that we don't do mistakes in these type of event sourcing system? We do mistakes. We might have wrong events, but what do? We drop another event which we call compensating event. So let's say I gave you 10 crowns by mistake. I cannot reverse it now. How do we solve it now? You know what you will do? You will send it back to me. So this is like a compensating event.
I'm not sure I'm going to do that, but yes, you could do that.
Well, it depends on the amount, right?
Yeah.
If the amount is too much, probably you won't do it. I would not do
No.
it. Yeah. Okay. Yeah. So this is the projection part that I was mentioning earlier. So we will be doing projection. There are different types of projections, by the way, state-based projection and event-driven projection. And I think I will explain it right here so that we have a good context, like why we are using it. So what is a state-based projection or state-driven projection, I should say? So in the state-driven projection, what we do, we have a process which is outside the database and polling the database if there is any change. So we might have a different column. If we talk about like a relational database language, we might have a column that is giving you, okay, ready for sync, or like not synced yet, or something like that. Some Boolean property probably you have in there is a column that you can poll and see all those rows that are not populated to the read side. That system or that polling agent will actually go and bring that and sync it to the read database. So you can, I think you already guessed the problem with this polling approach. This is not scalable, right? Another issue is the sync is not immediate. Your sync is dependent on the polling frequency. So if you're doing polling every 5 seconds, then your sync is 5 seconds late always. Okay. If you increase the frequency, like let's make it every second, now you're putting a lot of pressure on the database. A lot of pressure on the database now. So, I mean, there is always a trade-off and drawbacks in this type of approach. Second thing is, as I mentioned, they don't scale well. But the event-driven projection, which is my favorite, by the way, and I recommend everybody should use event-driven projections if you're using CQRS. So what happens? Your database becomes the event submitter or publisher. And in AWS, we can actually use streams. We have streams almost in every database, like QLDB, we have QLDB streams. In the DynamoDB, we also have DynamoDB streams that we can leverage. So in QLDB, what we can do, we can send all the records, changes, all the changes that we are doing into the QLDB, they will be streamed to Kinesis data streams. And then we have at least once delivery, and we might have out of order transactions. And for that, we need to make sure our receivers, for example, this receiver here, which is a Lambda function in this use case, has to be idempotent. That means we should be able to receive duplicate events and still be able to process it successfully without destabilizing the state of the system. So that is one very important property that we need to have in our receivers when we are dealing with the system, which is at least once delivery. There are few more delivery guarantees, like at most once or exactly once, but the most popular one is the at least once delivery, because that is much better, much safer to use in a lot of systems.
And in the bank example, that means we shouldn't process the same withdrawal or account event more than once. So it shouldn't withdraw 10 kroner twice, for instance.
Yeah, although I would be very happy if this is the problem with the deposits. So we get double deposits, right?
That's true.
I don't know if that bank will survive for long.
Probably not.
Yeah. So yeah, that you're right. We need to make sure the receivers are idempotent. That means they should be able to handle duplicate messages. All right. I think enough with the talk, right? Shall we jump to the demo? Okay.
Let's get to it.
Yeah.
So in the meantime, if you just joined us, this is the AWS Nordics office hours with me, Gunnar. I'm joined by Muhammad today, and we're looking at CQRS for purpose-built databases.
All right. So now you're looking at the AWS console, and I have already created a QLDB ledger. So QLDB is a cryptographically verifiable, immutable, transparent database. Very interesting database, and whatever we store in the QLDB actually never disappears. It's an event sourcing system. We can also call it system of record application or system of record database. So system of record database and event sourcing are the same thing. So rather than storing the current state of a system, what do? You store each and every event that is happening in the system into the database. So now you're looking at the AWS console, and from the left side, you can see I have ledgers, query editor, streams, export, verification. There are different features. As I mentioned, you can do the verification even on the QLDB. We will not go into the detail that much detail today. But few interesting things that I would like to show you is the ledger. So you can create a ledger very easy by clicking the create ledger button, or you can do all this that I'm going to do today with the API calls or SDKs or your favorite CI/CD tool or your infrastructure as code, whatever way you want. But why I'm using console? Because it's a little bit easier to conceptualize and like share what we are doing here. So if I click create ledger, we will not create ledger today, by the way, because I have already created one ledger for you. But creating ledger is very simple. You give the ledger name, permissions, and encryption. That's it. It's a serverless, cryptographically verifiable, transparent ledger database. You
So
don't need
yeah, so you don't have to think about the number of instances or how it's going to scale or things like that.
exactly. So it's completely serverless. So you don't even have to think about even instance size, not only number of instances and so on and so forth. But we will not create it because it takes a little bit time to create. So I will cancel this. And I already have a ledger, which is any company. Any company, I will tell you about any company soon. So what any company does, any company is a car sharing company. So you can use your mobile app. It's a fictitious company. You can use your mobile app. You can actually unlock the car, drive it. When you're back, your amount will be charged based on duration, like how long you have been keeping that car with you, and number of kilometers that you have traveled. So there is a very interesting formula that I invented to calculate the price. So what we are going to do today in this ledger, this is the ledger, this is the write side or the command side in CQRS, where we will write all our events. And when we return the car or when the trip is completed, let's call this thing trip. So when the trip is completed, we have to calculate the price, right? But calculating the price from an event store is very difficult because now you have to look at all different events that has happened during this trip. Let's say you unlocked the car, you were driving the car, you stopped somewhere, you refueled the car, you did a lot of things during your trip. So that means we have to like traverse all these events all the time. So what we will do, we will create a materialize view. That means we will calculate the price and put it in the DynamoDB. And then from DynamoDB, we can read it very fast, much faster than reading it from the QLDB, and we can actually read it as many times as we want. Because it's very important that when a trip is completed, when our journey is completed, we are not much interested in the events of the journey as such, right? But we are interested in how much did it cost. So that's why we want to make sure we separate these write and read use cases. All right. So let's go into the any company. I have already opened this ledger in the next tab. So here you can see it's the same ledger, any company. You can see here. And I have already prepared some queries for you. For example, we will create a table called trips journal because this is where we will write about our trips. And you do not have any table right now in this journal, right? So what I will do, I will just run it and you should be able to see a table creating on the left side. Okay,
And
we need an index.
the the queries you're doing now, are they more or less standard SQL queries?
All right, very interesting question. Actually, they are SQL-like queries. Actually, we call it particle, and particle is it looks like SQL, but it's a different type of query. And we can use particle with DynamoDB. We can also use particle with so many other databases, and it's an open source query language, and very similar to SQL. So you should not be able to. You should be able to like write or understand these queries in a second if you already know about SQL. All right, next we need to create an index. And why do we need index? Because our queries or the retrieval or reads on this side, on this database, are much faster. Also, we need some indexes to help QLDB partition our database in a right way. So that is the purpose here. So what I'm doing, I will be using trip as a partition key or the index column here. So let's run it. And now you should be able to see index under the indexes, you should be able to see we have index on the trip ID. Okay, now let me insert our first trip. So there are different ways to insert the trip. I can use the query or the particle here. I can also send it via the REST API. If you remember from the diagram I showed you, I showed you the application gateway, like traffic was coming through application gateway, and then it was going through a Lambda function and then coming to the QLDB. All right, I will show you that part as well. But let's send our first query or first trip information, which is the trip started event, into the system. So let me select it, and then you can see the document was inserted successfully. All right, how does this look like? So we can actually query it like any SQL statement. The particular statement looks like similar. So here is the trip one, and it's already there, and we can see it as IN. And what is this IN thing now? So IN is a JSON-like serialization format, and there is nothing more to it. It's very simple. It's much more easier to serialize and deserialize. So internally, QLDB is storing all the data in the IN format. All right. So now this data or this record or this trip record is already in this QLDB. But honestly, this record is not only in the QLDB. This record is already available in the DynamoDB, and I'm super confident about it. Let me show you where. So you can see there are no items here because I ran this query before starting our session today. So if I refresh it, you should be able to see this data here. So how does this data came to DynamoDB? That is the question.
I think we know based on the architecture, but, let's
Exactly.
see if that's correct.
Okay, you broke the suspense.
Yeah.
Anyway, so this is the read side. This is the read database because this is read optimized. We can actually cleverly make partitions in DynamoDB and have very cost-effective queries, very fast queries, and it's key value database. So lookups are super fast. And this is not only about DynamoDB. If you could use any other purpose-built database as well. For example, I could use OpenSearch for that as well without any problems, but the same architecture. So, but we are picking the DynamoDB today because it's your favorite, Gunnar.
Yes, thank you.
Okay, so the projection, this is the projection part. So how this projection is happening. So what we are doing actually behind the scene, the projection is coming with the help of a Lambda function. I will show you the Lambda function code in a minute as well. So what I'm doing, I'm using QLDB streams. So in this third tab, I have already opened this link, streams, and you can see I configured a few 2-3 streams before running this demo. And now this is the active stream that is actually sending all the data via Lambda functions to DynamoDB. And in the DynamoDB, we are not storing all the information that we have in the QLDB. What we are storing is what is the current meter value and how many kilometers we have driven so far and what is the price. And you see they are not completed yet. Reason is we are still driving. We started the trip. We did not end the trip yet. All right. But let's end the trip with the API, not on the particle side. And for that, I have already created a command, all right, that we will send. And this command will actually go through API gateway, land on the Lambda function. Lambda function will use QLDB driver. So when you are working with QLDB programmatically, you use drivers. So different languages have their own drivers. So with the help of QLDB driver, you will be able to commit these transactions in QLDB. So since we started with trip 1, so let me change it a little bit. So we actually end this trip. So what I will send trip completed event. All right. So if I send this, actually this URL is the, you know, our API gateway URL, and we should be able to get back a positive or OK response. And in this case, I'm getting back 202 accepted. Do you know why did we receive 202 accepted, not 200 OK? Because is it eventual consistent, right? Because we don't know yet.
Exactly.
Okay, so let's prove it. Whether do we have this projection working correctly or not? So I will do this refresh one more time. And now you see we have the values for kilometers. The price is already calculated. All right. And rest of the information is pretty much same because I did not change so many things. So now you see we can easily read the pricing or cost part of this system from the query side. We don't even have to go to the right side anymore. We will be able to do all this from the DynamoDB. And we don't even have price on the QLDB side at all. There is no column that says what is the price. In QLDB, we are just storing these events like trip started, trip completed, drive started, drive stopped. We can actually do a lot of analytics based on all these events. And when we have to do some querying, we can actually send it to OpenSearch, we can send it to DynamoDB, DocumentDB, Graph database, wherever we want to send it to. And then the queries are very fast. All right. What about reading the query from the API? That is also very simple. So what I will do, I will just check for trip 1, right? And send this to our API gateway, and API gateway will talk to Lambda function, and then Lambda function will get back this data to us. From where? Not from the QLDB, but from the DynamoDB. All right.
So now we're using the bottom path of the architecture slide.
Exactly. So let's go back to the architecture slide one more time. So what I have done, I have shown you like how commands are going to the Lambda function with the help of API gateway. Then we use QLDB driver, right? Persist the command if command is accepted as an event into the QLDB. From QLDB, the event is emitted or sent out as a stream to Kinesis data streams, and then Lambda functions picks it up and then adds this materialize view or the query side into the DynamoDB. And then similarly, we can actually read it through the Lambda functions. And by the way, if I want to read all the different historical events, I can still do it with the help of QLDB. But this type of query is very rare. People do not want to see all what happened during the trip. They are most likely are interested in the trip cost thing. All right. So shall I show you the code a little bit?
Yeah,
quickly?
please.
All right. So now I am on. You can already see what we are doing here. So this is the Lambda function that is receiving the trip commands. So that is the upper part of that architecture diagram, if you remember. And I told you how Lambda function is working. Lambda function is actually using nothing but the QLDB driver. And if you look at it, most of the code here is the boilerplate code. And that's it. This is the total code I'm using for doing all that. It's very simple. It's a boilerplate code. You just instantiate the driver, you build the driver, and then run transactions on the driver. Anything which is between this transaction scope is atomic. That means if you get exception anywhere, the things will not be committed to the database. So it's very, very easy to actually work with this. And then you can prepare queries, you can do insert queries, you can do update queries, whatever you want to do here. It's very easy, very, very simple. And since it's just a demo, I'm not following a lot of best practices here because I just want to make sure you are able to see how quickly I can spin up this type of demo here.
And you don't have to use C#, right?
Yes, obviously. I mean, C# is my favorite language. That's why I use C#. But you can use, because drivers are available in many different languages. So you can use Python, you can use Java, Node.js, whatever you're comfortable with. And I'm using C# because I like it, and it's more natural that I can write much faster in it. All right, so this is the one part, like one side, what about the query side? So we also have query code for the query, which is pretty much similar. Actually, there is not much difference. So let me bring that up. So look at the query side now. There is nothing more than this for querying. So what I'm doing, I'm just looking at the get function because I just want to ignore all other functions. I receive data from the API gateway, and here I'm using DynamoDB client because now I'm on the read side. I'm not on the right side where we are writing. So DynamoDB client, I'm just doing a quick load and then sending you back the data. That's it. And my model is pretty much decorated with like what is the partition key, what is the range key, and things like that. And that's it. This is the total code that I have done. And if I go back to my slides, all this architecture that you see is serverless. And it's very low code development. But I'm able to do a very good system. I'm able to create a system which is reliable, transparent, cryptographically verifiable, and it's a system of record. And we have separate writes from reads, and reads are very fast, super fast. So in a very short period of time, I was able to develop that.
So we have a question which I think it fits really well right here. From Shield Jaguar, is there any recommendation for debugging or tracing CQRS based architecture?
Yeah, so debugging, I mean, when you have CQRS, I think then you have a single responsibility principle applied in next level. So when you have write and reads together, you have more code at one place. But when you do CQRS, you have write code is separate from the read code. That means you can independently test them or independently even debug them, right? And when you have a problem in one of the systems, you will already know, okay, which system has a problem. Your writes will still continue. So that means it's more resilient as well. But testing or debugging is very simple. You just do debug. You just debug just like you do debug with any other system. I mean, CQRS will not do any changes in your debugging process here. And tracing, when you're doing tracing, in cloud, it's a distributed system, and probably the write and read sides are not even deployed on the same system or same architecture. For example, now I have two different Lambda functions, one for writing and one for reading. That means you need to have proper logging, you need to have proper tracing. And one more suggestion I have for you, when you work with any distributed system, actually you should initialize the request ID at the edge of the entrance when the message or the request gets into the API gateway, let's say in this use case or in this architecture. So the moment your request is entered into the system, you need to have a request ID. And then you keep that request ID, follow it along all the different pieces. Like in the Lambda function, in the queue, if I had any queue, as you mentioned, Gunnar, earlier, like we could have a queue here. We would like send that message ID in the message together with the message in the queue, and then that message request ID will follow along all the way. And that's how we should be able to trace where is where is the message.
And speaking of that, do you see at scale, is there a reason to think about using queues for receiving that command to begin with?
Exactly. Very good question. What if you throttle the quantum ledger database? Let's say you have a lot of writes, right? So first reason to use any kind of queue is the load leveling. So if your producers or if your clients are like bombarding with messages to your system, you want to make sure that you are able to handle them. So first use case is the load leveling, and that you can achieve with the queues. And then another use case is like you want to offload or decouple your subscribers from your publishers, that because then it will be even more scalable. So rather than like this Lambda function, for example, is sending all the requests to QLDB, probably we could actually send these commands to the queue. The only purpose this Lambda function would do is to validate the command. whether we want to reject this command or not. If we don't want to reject this command, that means it's a valid command. Then we schedule it on the queue, and another Lambda function can pick it up from the queue and then perform all the task. One more reason we could use the queuing is the retry. So when we have something on the queue, we can always retry. We receive it from the queue, we try it. Let's say if we have a transient error, and transient errors are, by the way, very common in distributed systems. If you know about the fallacies of distributed systems, one of the fallacy is network is reliable. So fallacy means that is wrong, that is not true. So network is not reliable in any distributed system. So if we have a queue, the moment you are able to persist the message in the queue, that means now your message is durable. You achieve the durability here. Now your receiver can receive the message and try to insert it into the QLDB. And if due to certain transient errors or network problem or anything for a while, you can retry that message. And that is the beauty of involving queue. But when you have a listener or a subscriber, that has to be idempotent, as we mentioned earlier.
So when wouldn't you use this pattern then?
Okay. There are some cases where we might not want to use CQRS, and one of them, or one important one, is when you cannot tolerate the eventual consistency, right? That is one
And
reason.
what could that be? Can you give an example when a single millisecond is too much?
Yeah, actually, eventual consistency does not mean. I would like to answer your question in a little bit better way here. So there are a few things when we speak to business about eventual consistency. Honestly, most of the time they do not understand what does it mean.
Hmm.
They think eventual consistency means no consistency, right? So there is a concept called weak consistency and
Yep.
eventual consistency. Weak consistency means your message get delivered, but eventual consistency is different. Eventual consistency is a strong consistency with the replication lag. So eventual consistency means it's a strong consistency with the replication lag, or the projection lag, or synchronization lag, whatever it is. And that lag is usually in milliseconds.
Hmm.
Usually in milliseconds. And depending on how you design your system, that lag is very, very negligible. And I mean, if you don't tell the business or anyone that it's an eventual consistent system, they will not know it, right? And one or few milliseconds or single digit millisecond is much smaller amount, like you can't even experience it.
So yeah, so that's an example of when not to use CQRS. Are there other examples?
All right, so the eventual consistency is the main example when you cannot use CQRS, because CQRS splits or decouples writes and reads,
Hmm.
and now you cannot use it, right? Another reason, possible reason, is CQRS introduces a little bit complexity, right? That means before you had only one team, you had a read and write together, and everything was fine. But now you have to have a separate deployments for your read and write,
Hmm.
because they are totally different, right? That means your team has to handle more moving pieces. And if you remember the question, somebody asked very interesting questions about debugging and tracing. That is another drawback, right? Now we need to implement some kind of distributed tracing here, because it's not a single system, or they're not together anymore. Especially the CQRS version that I'm talking about is very different than sometimes other people develop. So CQRS, what I'm trying to suggest is total separation, even the deployment level. You can deploy your read side independent of your write side, because you have different databases, and they both read and write are totally decoupled, and they are connected with the help of this projection mechanism. That's why I'm interested in this event driven projection rather than state driven projection, because now you can deploy reads and writes independent of each other. So when you have this type of situation, obviously it will add complexity. You need to have people who understand this. You need to have better tracing, logging, observability, all that in a better way here. So that is another reason why you don't want to do this if you think it will be difficult for your teams.
All right. So then, closing top of the hour, we're approaching top of the hour, so time to wrap things up. Any final things you want to add, Muhammad, around CQRS and or purpose-built databases?
Yeah, so what I would like you to do, explore purpose-built databases and choose the database based on your use case and the query pattern, rather than choosing the database which is your favorite, right? So this is not a good strategy to choose the favorite database. Always choose the database which is right tool for the job. And when you have a different databases, one more thing I would like to share here is some people think when you are working with microservices architecture, then you need to have only one database per microservice, because there is a pattern called one database per microservice, right? So people think, okay, we cannot have two databases for one microservice. And this is where I want to challenge people, like, go think a little bit more. We can have multiple databases per microservices as well, as long as your microservice is as long as you're not exposing those databases outside the microservices. That's totally fine. You should have you can have multiple databases per microservices, and you can choose database like I chose QLDB and DynamoDB based on a specific use case. But if you look at it, the entire use case is one microservice. It's not a monolith. It's one small microservice. It could be a part of a bigger system or ecosystem here. So choose multiple database, and everybody gets a database. Yeah.
Yeah, I think that's the the wrap up for this show, maybe. All right, cool, Mohammed. I really like this. I think it was a great episode to look at CQRS for purpose-built databases. So thanks to you for joining today on the final episode of the season. Hopefully we'll be able to do some other episode in the fall, maybe. And I also want to thank all of the viewers for joining not only today, but for the entire season. Of course, we've had lots and lots of great episodes throughout. So with that, thank you, Mohammed.
Thank you very much. Thanks a lot.
Thank you, all the viewers. And I see now that my outro slide is going to say, see you next Monday, but I won't see you next Monday, but I'm going to use it anyway. So Thank you all, and bye-bye.